Hello and welcome to the concluding session of the course Antennas. Today I am not going to take lectures, but today we are going to show you various experiments which we have performed on different types of antennas. We have designed so many antennas, we have fabricated so many antennas. So, today I am standing inside the antenna lab of Electrical Engineering Department, IIT Bombay. So, my students along with the TS, they will show you different types of antennas which we have developed at IIT Bombay. They will also show you how to do the input impedance measurement, VSWR measurement using vector network analyzer. After that, they will also show you how to do the radiation pattern measurement. Now, most of the time people do radiation pattern measurement inside an anechoic chamber using automated measurement tool. However, those are very expensive and not possible for all the people. Then what do you do? So, all you need is really is a somewhat an empty room, put a transmitting antenna, receive antenna, and you can do the measurement even in the open room also. So, we will show that in an open corridor, so that you can actually see the pattern measurement as well as the gain measurement. And for gain measurement and especially the half power beam width, even an open room is good enough. The problem where we have in the open room is most of the time the null depth may not be very sharp, or the cross polar level which are below minus 20 dB, they may not be good, but otherwise gain measurement as well as the half power beam width and other things are perfectly fine. So, I hope you will enjoy the show, see the antennas and see all our young and enthusiastic students as well as TS to show you various antennas and how to do the radiation pattern measurement and impedance measurement of the antenna. So, thank you, and I hope you enjoyed the show as I enjoyed recording the show. Thank you very much, and I hope you have enjoyed this entire journey, and rest of the journey enjoy with my students. Thank you.
Now, we are going to show various antennas available in our lab. So, this is a dipole antenna, this is a loop antenna, these are some microstrip antennas, circular microstrip antenna, arrays. This is a 2 by 2 microstrip antenna array. This is a 3D printed horn antenna. This is a helical antenna. This is a horn antenna designed at 1800 megahertz. There is a electromagnetically stacked microstrip antenna. Planar log periodic antenna. This is a E-shaped microstrip suspended antenna. These are some of the antennas available in our lab.
Hello everyone, I am Rinki Chopra. I am a PhD student in Antenna Lab. I am also a teaching assistant for this course. So here we are going to show you the basic antennas: monopole antenna, dipole antenna and loop antenna. This is dipole antenna designed at 800 megahertz. Here balun is used to feed the power, that is used to provide the differential feed. This is a planar monopole antenna. Here this is tapered to widen the bandwidth. This is a loop antenna designed at 800 megahertz. Here balun is used to feed the power.
Hi, I am Anamika Verma. I am a PhD student. These antennas are designed at 2 gigahertz. This one is square microstrip antenna and this is circular microstrip antenna. These are the compact versions of the circular microstrip antenna with shorting posts, and in all these antennas power are fed by SMA connectors.
Hi, I am Pratigya Mathur and I am PhD student at Antenna Lab in IIT Bombay. Microstrip antenna have a limitation of low gain. This limitation can be overcome by designing antenna arrays. Antenna arrays can be of two types: corporate fed antennas and linear fed antennas. This is 5-element linear microstrip antenna array. The other type of array is corporate fed antenna array. This is a 2x2 corporate fed antenna array designed at 5.8 GHz. To increase the gain further, 8x8 corporate fed microstrip antenna array has been designed at Ka-band. This antenna array finds application for satellites and defense purposes.
Hello everybody, I am Lieutenant Colonel Sandeep Das, presently doing my MTech at IIT Bombay. I will be introducing the two conventional techniques which are used to broaden the bandwidth of microstrip antenna. Firstly, this is a gap coupled microstrip antenna designed for 3G band, and secondly, this is a electromagnetically coupled stacked antenna which is also used for broadening the bandwidth of microstrip antennas.
Hello everyone, my name is Debpratim Ghosh and I am currently a PhD student at the Antenna Lab at IIT Bombay. So today I have got for you a stacked patch electromagnetically coupled microstrip antenna, wherein we have this bigger square as the ground patch, and on top of that we have the main radiating patch which is in the middle, if you can see this, and finally on top we have the parasitic patch. So this is designed to work primarily for the GSM 900 band. So its bandwidth is roughly from 890 to about 1000 megahertz. So if you recall, the GSM band itself is from 890 to 960 megahertz. So this is a simple example of how you can use a microstrip antenna with two patches to obtain a comparatively higher bandwidth. Thank you.
Hello everyone, my name is Anil Kama. I am a PhD student at IIT Bombay. Till now my friends have shown you a planar antennas, and now I will show you 3D printed antennas. So these are some of the examples of 3D printed antennas. So here this is a simple horn antenna made using 3D printing technique. Similarly, there is another antenna using 3D printing technique.
Hello, I am Rohini Bhide, working in Antenna Lab. This is reflector antenna which is available in market. It operates at 2.45 GHz. It provides us 24 dBi gain, which can be used as a high gain application. To make it lighter, the strips are used instead of having a metallic plate.
Hello everyone, I am Hemant Kumar, teaching assistant for this course. I am here to present some of the antennas designed by us. This is a basic planar Yagi-Uda antenna designed at 1.12 GHz. It is designed on a FR4 very low cost substrate. It have a approximately gain of 6 to 7 dBi. Next is a broadband planar log periodic dipole antenna. This is a dipole arrays, and you can see here is the radiation pattern, and here we have to feed the antenna. This is a coaxial feed planar log periodic dipole antenna. This is a helical antenna. Here is the feed, and this is designed for FM. Next is horn antenna. This is our horn antenna designed for 1700 megahertz to 1900 megahertz. It have approximately gain of 11 dBi. It have a feed from here. This is a feed probe feed. So you can see inside, and here we can see there is a coaxial feed. Now we are going to show you how to measure the input impedance, VSWR, and reflection coefficient for a given antenna. For measurement, we have to use a network analyzer. Here we have a network analyzer which can operate from 100 kilohertz to 8.5 gigahertz. So we can measure the antenna which have any frequency range from 100 kilohertz to 8.5 gigahertz. So first step to measure the input impedance or VSWR or reflection coefficient, we have to calibrate. So to calibrate, we have given some standard loads. One is open, short, and 50 ohm matched load, because the maximum value of VSWR can be infinity or minimum is 1. 1 is for complete matched load and infinity is for open and short load. So we will require 3 loads. One is open, another short, and the last one is 50 ohm matched load. Now we will do the calibration.
We designed this antenna
for GSM band, so let's select the frequency range. So let's first select the frequency range, press start, then select the start frequency as 800 megahertz, then select the stop frequency, that is roughly select 1.1 gigahertz. Because this antenna is designed to operate from 893 megahertz to around 980 megahertz. So we need to select the frequency range that should be little higher than this or lower than the start frequency. So that is why we are selecting the start and stop frequency as 800 megahertz and 1.1 gigahertz. Then we need to calibrate. So in order to calibrate, select the calculate number, go to calibrate. For this we need to select the calculate. So the calculate number is 85515A, select calculate number, then press calibrate, then do one port calibration, because here only one port we are using. To do the calibration, firstly connect it with open. After connecting, press OK, then connect it to short, again press OK, and after that connect it to load, then press OK. Now you know when you connect it to open, it provides 0 dB return loss. So here it is providing 0 dB when we are connecting to open, and same is in case of short. When we connect it to load, then it provides us very less reflection coefficient. So practically when it comes below 20 dB, then we say that it is calibrated with load. So the thing is, why we do calibration? So calibration is usually done to account the cable losses. So far we have calibrated the cable and we have done the full calibration for this operating range. Now we need to connect it with the antenna. Here I have connected it with the antenna. Now you can see here, in this my response is coming below 10 dB in some frequency range. That is my operating band. So we need to see what is the bandwidth that it is providing. So we need to put some marker so that we can see what is the operating bandwidth that it is providing. So just select marker and put it at minus 10 dB endpoints. So here we are providing two markers to select the 10 dB points so that we can get the idea of the operating bandwidth. So the bandwidth that we are getting here is from 900 to 1.01 gigahertz. That is my operating bandwidth for this antenna. Now if we want to see the dip, then we need to put one more marker and then need to see the lowermost point. So the lowermost point that we are getting here is at 1 gigahertz. So this is my frequency range. Now if we want to see the Smith chart plot or impedance plot, then we need to select the Smith chart from the format, go to format, then select Smith, then select the format R plus JX. Now you see here one loop is coming. This loop is coming because of the parasitic patch that is placed over here. So there is a coupling between these two patches. So that is why the loop is created in this Smith chart. Now I would like to show the VSWR plot. We need to select the SWR. So here you can see the VSWR plot. So whatever range is coming below 2, that is my frequency range for this antenna. From here you can see from 900 to approx 1 gigahertz my range is coming. So that is my frequency of operation for this antenna.
Now we have shown and explained how to measure the impedance, VSWR and reflection coefficient. Next we will explain how to measure the gain and radiation pattern for a given antenna. We will use one reference antenna over the same frequency range. Now let us see how to measure the radiation pattern and gain. Here we are going to measure the radiation pattern and gain of the given antenna. The given antenna is working at 900 megahertz. This is a suspended microstrip antenna working at 900 megahertz. So before doing the measurements, we should have some reference antenna with respect to which we will measure the gain and radiation pattern. So we have chosen this reference antenna which is working at the same frequency range. This is a horn antenna. Its gain approximately 10 dB at 900 megahertz. To calculate the gain of our given antenna, we will first place these two antenna at far field distance. The far field distance you can calculate using the formula 2d square by lambda. So at 900 megahertz, if you calculate the far field distance, it will be approximately 1.8 meter. So we have taken approximate distance of 2 meter. So the distance between these two antennas is 2 meter. This is our given antenna, this is our reference antenna. In the reference antenna, we will provide the input. Input can be generated from the network analyzer, it can be generated using our signal generator. So to give the input to the reference antenna, we will use signal generator. This signal generator works from 100 kilohertz to 6 gigahertz. So it lies in our frequency range. So first we have to select the frequency at which we have to give the input. So select frequency, click on this. Now select the frequency value. If we want to measure gain or radiation pattern at 900 megahertz, then we have to give the input as a 900 megahertz. Next is we have to give the some amplitude value. Amplitude, you can select 0 dBm, 10 dBm. The maximum value that we can give from this signal generator is 17 dBm, but we are going to use as a 10 dBm. So select amplitude level which is 10 dBm. To give the input to the reference antenna, we have to on this button, RF on. So press this button. So we have clicked on this RF on. Now the input is given to our reference antenna. Till now we have provided the input to our reference antenna. Now this reference antenna will radiate, and this given antenna for which we want to measure the radiation pattern and gain will receive the signal, and the received signal will be measured using the spectrum analyzer. This is spectrum analyzer. It works from 9 kilohertz to 3.6 gigahertz. So our selected frequency is 900 megahertz. So we will set the frequency first. So from this you can select frequency. Now you have various options: center frequency, start frequency, stop frequency. So we can select start frequency first. Now set this start frequency. You can set it at 850 megahertz. The next is stop frequency, 1 gigahertz. So we have selected our frequency range. Next, you can change the amplitude reference level. So to change the amplitude reference level, select amplitude reference level. Take reference level as a minus 10 dBm or 0 dBm. So let us take minus 10 dBm. So this is our reference level. Now you can see approximately 900 megahertz we are getting some peak. You can measure this received value by selecting the marker. This is our selected marker. So at 900 megahertz you can see the value is minus 11.4 dBm. So you can say the received power at 900 megahertz is minus 11.4 dBm. Now to calculate the gain of our given antenna, we have to use Friis transmission equation. So Friis transmission equation will give you the gain of our antenna. So there are various parameters. PT is transmitted power, which we have used as a 10 dBm. Next is GT, the transmitter gain, which is a reference antenna gain, which is approximately 10.7 dBi at 900 megahertz. Next is GR. This GR value we will calculate from this equation. Lambda is a wavelength which can be calculated from C by F. C is our speed of light, frequency, F is 900 megahertz. So you can calculate the wavelength. Next, R. R is the distance between the reference antenna and the receiver antenna. Receiver antenna is the antenna for which we are going to calculate the gain. We have taken the distance between these two antennas as 2 meter. So next, we have connected the transmitter antenna to the signal generator and the receiver antenna to the spectrum analyzer using the coaxial cables. So these coaxial cables have some losses. We have included these losses, which is approximately 3 dB. Now you can put these values in this equation. You can find out the gain of the received antenna. So the gain of the received antenna calculated from this equation is 7.8 dBi. Till now we have measured the gain of our given antenna. Now we will measure the radiation pattern. To measure the radiation pattern, we will first align these two antennas. One is our given antenna for which we are going to measure the radiation pattern. Next is our reference antenna. There are 4 types of radiation pattern you can measure. First is E co-pole, in which both the antennas E plane should be perfectly aligned with respect to each other. So this antenna E plane is in vertical direction. This is our reference antenna, also have E field in vertical direction. So in this we have both the antennas E field in vertical direction. Now to measure the E plane co-polarization, we will rotate our antenna from 0 degree to 360 degree with respect to the reference antenna. At 0 degree, the received value will be maximum. So for other values of the angles, we will normalize with respect to the 0 degree value. Now if we want to measure the cross pole, we have to rotate this antenna by 90 degree in vertical plane. Then you rotate this antenna 0 degree to 360 degree in the horizontal plane with respect to the reference antenna and take the readings. The readings will give you the cross polar in the E plane. Similarly, if you want to measure the H plane co-polarization, we have to align both the H planes in the same vertical direction. So we have to rotate this reference antenna in this direction. So this is our H plane. Similarly, we can rotate this antenna by 90 degree, which will give us the H plane in the vertical direction. Then we can do the same procedure for the radiation pattern. If we want to measure the cross pole in the H plane, then we will rotate this antenna in the 90 degree. After that, rotate 0 to 360 degree in the horizontal plane with respect to our reference antenna. This will give you the cross polarization components in the H plane. We will show you the demo for the E plane co-polarization components. So to rotate this antenna, we have one rotating table. Here there is button. To rotate this antenna, if you press this button, it will rotate our antenna by the value mentioned in this screen. So you can see the antenna is rotating by 1 degree angle after every step. So now we can see the value in the spectrum analyzer. So after rotation of 20 degree approximately, you can see the received value is decreased by 1.3 dB approximately. You can see minus 12.8 dBm we are receiving. At 0 degree, we have received the value approximately minus 11.4 dBm, and now the value is minus 12.7. Again, if you further rotate, this value will further decrease. Now we will take the reading at 90 degree. Now we have rotated our given antenna by 90 degree with respect to the reference antenna. Now we can see the reading what we are receiving. So the received value you can see is approximately minus 23 dBm, which is approximately 11 to 12 dB less than the maximum value. Now we will rotate this antenna further by 90 degree. Now you can see we have rotated our antenna by 180 degree with respect to the reference antenna. Now the received power will be less because this antenna is pointing opposite to the reference antenna. So now the reading is approximately minus 30 dBm for 180 degree angle. Now if you want to calculate the front to back ratio, front value was approximately minus 11 dBm and the back value which is at 180 degree is approximately minus 30 dBm. So if you find out the front to back ratio, it will come out to be equal to 20 dB approximately. We have measured the radiation pattern from 0 degree to 180 degree. Because the antennas are symmetric, so there is no need to calculate the radiation pattern from 0 degree to minus 180 degree. So you can use the same values that we have obtained from 0 to 180 degree and plot the radiation pattern using available softwares. In the similar way, you can find out the cross polar for E plane, co-pole component in the H plane, cross polar component in the H plane. So you can obtain all these 4 plots. Thank you.